So let's start. So last time, if you remember, we were doing what? Yes, but beyond that, we were doing rockets. Remember, we were looking at how can we analyze quantitatively the motion of a rocket. So if you remember, a rocket is basically something that throws out mass, and consequently that thing accelerates. Okay, so you have a rocket which essentially typically is going to burn some fuel, is going to expel some exhaust gases rapidly with respect to the rocket, and consequently it turns out, and this is a consequence of Newton's laws, that the rocket will accelerate. Okay. So how do you quantitatively analyze this situation? As usual, you draw two snapshots, because what you're interested in is applying that the external force on your system equals the rate of change of the linear momentum. So you take two snapshots of the situation with some small time interval. You look at the linear momentum of your system at the initial time, you look at it some time later, you take the difference in the linear momentum, you divide that by the time interval, take the limit that the time interval goes to 0. That's essentially your right hand side. You set that equal to the external force acting on your system. Okay. So if you are going to apply this to your rocket, what you do is that at time t, you say that the mass of the rocket is capital M, and the rocket is moving with some velocity vector which you call v. Just for diagrammatic reasons, I've drawn this v to be pointing upwards. It could be pointing in any direction whatsoever. That's why I put this arrow on top of v. V is your velocity vector for the rocket at time t. At time t, the mass of the rocket alone is capital M. So capital M is actually a quantity that is changing with time. A short time later, at time t plus delta t, the situation in general is like that the rocket has a slightly smaller mass. So the mass of the rocket is m plus delta m. Delta m is negative because the mass of the rocket is decreasing. To apply F is equal to dP by dt, remember you have to make sure that what you are treating as your system, the mass of that does not change. So once you have defined your system, stick to that definition. Over here, between these two snapshots, the mass of your rocket has changed. So this is not the full system that you were considering at time t. There's some part of the system that is missing. That missing part, of course, is nothing other than the exhaust gases that were expelled out. The mass of the exhaust gases is minus delta m, because delta m itself is negative, so minus delta m is positive. Another way to see that is that m plus delta m minus delta m will just be m. वो भी कर सकते हैं, okay? Right? Many people do that, except that then वो करोगे फिर dm by dt जो है वो आपका जब rocket का mass decrease कर रहा होगा, फिर dm by dt would be negative, right? Dm by dt would be positive if the mass of the rocket is decreasing. If you put in m minus delta m over here, which looks slightly weird, because if the mass of the rocket is decreasing, dm by dt should be negative. Okay, that's why most people prefer to do it this way. आप हमेशा f of x plus delta x करते हो ना, minus f of x. That's what you're used to. You could do it this way as well. Okay, fine. And over here, the velocity vector of the rocket is v. Maybe there's some change as well, delta v. Hopefully there is a change. That is the whole objective of throwing out these exhaust gases. That throwing out the exhaust gases brings about a change in the velocity of the rocket. Okay, so hopefully there is a change. If there is no change, this will tell you that there is no change. Okay, maybe the situation is such that whatever the upward thrust that is being produced by the expulsion of these exhaust gases, maybe that is equal to the gravitational force. In that case, the acceleration is 0. External force is whatever force is acting on the rocket due to something that is outside the rocket. Could be the earth, for example. Could be the gravitational force. Okay. Could be some other force. Okay, whatever. Okay. right? And then of course you have to take into account the velocity of the exhaust gases. You do that typically by defining the velocity of the exhaust gases with respect to the rocket. So just imagine, okay, that you have some arm strength. Your arm strength is fixed independent of whether you are moving in a train, whether you are standing on the ground, whether you are traveling on a ship. Your arm strength is not changing. So if you manage to throw a ball with a speed of 10 meters per second, okay, if you do manage to do that, that is always with respect to whatever you are standing on. But the speed of the ball that you have thrown will depend on what you are standing on. So if you are in a train, the speed of the ball that you have thrown will depend on the speed of the train. Your arm hasn't changed, of course. So that's why in exactly the same way, people who design rockets prefer to talk about the velocity of the exhaust gases with respect to the rocket, because that is what they can design. Just like you can design your arm by going to the gym. Okay, so essentially in the same way, rocket engineers can design an appropriate value for that what should be the velocity of the exhaust gases with respect to the rocket, independent of how fast the rocket is moving. Okay, so you define U, horrible notation, but this is standard. U is not the initial velocity of the rocket, sorry. U is the velocity of the exhaust gases with respect to the rocket. In other words, in our notation before, U is simply the velocity of the exhaust gases with respect to the rocket. But over here, of course, you're doing the calculation in the frame of the ground, because that's an inertial frame. The rocket is not an inertial frame. I mean, if it's a complete push-push rocket which never went anywhere, then it is an inertial frame, but that's not the point, okay? Hopefully it goes somewhere, okay? Beyond bookshelves, okay? But anyway, okay? So you have that you are looking for the velocity of the exhaust gases with respect to the ground. This, your rocket, there's an observer in the rocket, there's an observer on the ground, some exhaust gases are coming out. So then you have RER and REG and RRG, and it is obvious from this diagram that RRG plus RER equals REG. So REG must be equal to RRG plus RER. और as you have discovered, अगर इसको opposite order में लिख दो तो ये RR subscript cancel हो जाता है और REG आ जाता है. Okay? So you have REG and you differentiate this, you get VEG is equal to VRG plus VER. Exactly the same as the problem that we solved when we were doing relative velocity and you were throwing balls on a moving train. And you're looking at the motion of the ball from the perspective of somebody inside the train, from the perspective of somebody outside on the ground. Exactly the same thing. Okay? So this is what we have defined as U, and this keeps on changing with time. And in this snapshot, what is that? VRG. That is simply V plus delta V. यही तो हमने लिखा है. So the velocity of the exhaust gas with respect to the ground at time t plus delta t equals V plus delta V plus U. या ऐसे सख्त होता जा रहा है, okay? Anyway, so you have V, E. पहले बिजनेस स्कूल में माशाल्लाह से उन्हें 9 बोर्ड दी हुई हैं मुझे और उनमें से भी खराब हो गए 2 बंदा anyway. Velocity of exhaust gas with respect to the ground, ये भी edit कर देना, equals the exhaust gas with respect to ground equals V plus delta V plus U. Okay, delta V is the change in the velocity vector from time t to time to delta t. Change in the velocity vector of the rocket. Okay, हाँ. ये इधर ये B, ये RRG है. वो मेरे लाइन के साथ R जुड़ गया इसलिए आपको B लग रहा है. R rocket है. Position vector of the rocket according to observer on the ground. Okay? इधर मैं थोड़ा सा ठीक है. Okay, now it's just a matter of calculating the momentum in the before snapshot, calculating the momentum in the after snapshot. So remember, that's your objective. So you write down the momentum at time t of the system will be equal to, इधर क्या है momentum पूरे system का? ये तो red spot physics है यार. This is just mv. Remember, or either function क्यों time का? Because as time changes, m changes and v also changes. Okay. What is the momentum at time t plus delta t? This is beyond red spot physics. Okay, but try. This equals this thing multiplied by this thing plus this thing multiplied by v plus delta v plus u. वही तो निकाला है. The velocity of the exhaust gas with respect to the ground. So the velocity of this is v plus delta v plus u. So this is equal to m plus delta m times v plus delta v minus delta m v plus delta v plus u. This is the momentum of the system you have defined as the rocket at time t. उससे पहले जो exhaust gases निकली थी, never mind that. उसको भी आप consider कर सकते हैं exhaust gases that were expelled out before time t as part of your system, but they will be doing exactly the same thing in this snapshot. तो जब आप difference लोगे, those will essentially not contribute anyway. When you're looking at these two, what happens during time duration delta t, focus on what's going to change during time interval delta t. जो बाकी जो exhaust gases already निकल चुकी थी, वो इधर भी निकली हुई हैं. No change happened over there. The change is only because of the little small amount of exhaust gases that were expelled during time delta t. That's why only those exhaust gases I'm considering as part of my system. Okay, so at time t, the system is the rocket at time t, sirf the rocket at time t. At time t plus delta t is, I've defined my system as the rocket at time t plus delta t plus the exhaust gases that were expelled out during time delta t. ये वो वेक्टर मैंने लिखा है. ये हो सकता है ऊपर हो विद रिस्पेक्ट टू द ग्राउंड. आप अगर गाड़ी उस तरफ जा रही है 60 किलोमीटर पर आवर, आप उस डायरेक्शन में फेंको 5 किलोमीटर पर आवर की स्पीड पे बॉल विद रिस्पेक्ट टू द कार, विद रिस्पेक्ट टू द ग्राउंड बॉल की क्या वेलोसिटी होगी? 55 किलोमीटर पर आवर दैट वे. Yeah, sure, but to apply this, you have to make sure you consider the momentum of the whole system. नहीं, वो काउंट कर सकते हो, वो भी कर सकते हो, but that's not, या उनको इंक्लूड करते कोई फर्क नहीं आता, आपका आंसर सेम ही आएगा, क्योंकि what matters over is the change in the momentum. जितना जो बाकी गैसेस है, जितना उनका मोमेंटम इधर होगा, उतना ही उधर ही होगा. हाँ, तो मोमेंटम चेंज हो रहा है ना, बट उन जो एग्जॉस्ट गैसेस टी से पहले निकल चुकी थी उनकी वजह से नहीं चेंज होगा. जो एग्जॉस्ट गैसेस ड्यूरिंग डेल्टा टी निकली उनकी वजह से चेंज होगा. नहीं, एक्सटर्नल फोर्स लग रही है इधर. नहीं, हो सकता है कोई ग्रेविटेशनल फील्ड में जा रहा है ना रॉकेट. ओके, सो यू हैव ये ठीक है. This is the momentum of the system at time t plus delta t, mass of rocket times velocity of rocket plus mass of exhaust gases multiplied by velocity of exhaust gases. Okay, so now let's do it. Okay, अब आपने निकालना है change in momentum between the two pictures. Change in momentum will be equal to, अब बस आपने simplify करना है, m plus delta m, the mass of the rocket at time t plus multiplied by the velocity of the rocket. Your seniors, by the way, creativity knows no bounds. So just to clarify, this does not mean that this thing is a function of v plus delta v. This thing is just ordinary multiplication. ये m times v plus m times delta v plus delta m times v plus delta m times delta v ही है. Okay, and then you have minus delta m. Okay, times v plus delta v plus u And then I have something else. Minus mv. So this whole thing is the momentum at time t plus delta t. This is the momentum at time t. Put in the minus to take the difference. The rest is just simple algebra. You just get m times v plus m times delta v. This is really what you're interested in. कि वो एग्जॉस्ट गैसेस फेंक देंगे जिससे डेल्टा वी क्या आएगा प्लस डेल्टा एम टाइम्स वी प्लस डेल्टा एम टाइम्स डेल्टा वी सब कुछ ही कट जाएगा माइनस डेल्टा एम times v. Just be over here, be very careful. Don't be lazy and put something like this. Because then there's a very high chance that you make a mistake. This would imply a change in mv. A change in mv is very different than a change in m multiplied by v. So put brackets to denote ke bhai exactly kya kar rahe ho, okay? Don't be stingy with the brackets, okay? That's why I'm being very careful over here. Minus delta m times delta v. And then you have minus delta m times u minus mv. And now as in most physics calculations at this level, the intermediate results may look complicated and frightening, but things simplify very quickly. So first of all, इस चीज को तो गायब होना ही होना है. क्यों? या श्योर लेकिन सपोज का लिखना भूल गए थे आपका इमीडिएटली होना चाहिए दाल में कुछ काला है काला किधर से आएगी दाल में बिकॉज डेल्टा पी इफ डेल्टा टी इज स्मॉल डेल्टा पी इज गोइंग टू बी अ वेरी स्मॉल वेक्टर दिस थिंग इज नॉट अ स्मॉल वेक्टर so if the left hand side is a small vector the right hand side better also be a small vector so that's why you cannot have this surviving this better cancel out. And it does, of course. And you have m delta v. This better not cancel out. यही तो निकालना है हमने. ये delta v क्या है? Okay, what's the change in the velocity? Okay, this should cancel out. Why? Physically, क्योंकि this is change in mass times the velocity vector. The force that the rocket experiences should only depend on कि भाई exhaust gases को क्या किया. तो and it does cancel out. ये आपका ये और ये. This thing also cancels out. And you're left with two terms. जो दो terms रह गई हैं. These are the only two surviving terms. This is a change in the momentum. Okay, right? And then you have the delta p over delta t then equals delta t is the time interval between the two snapshots equals m delta v over delta t and then you have minus delta m minus u पहले लिख देते हैं चलो never mind who cares. ये zero नहीं है. Okay, in the limit where delta t approaches 0, this becomes m dv by dt minus u dm by dt and this must be equal to not 0, the external force acting on the rocket. This is what is known as the rocket equation. Okay, that essentially allows you to figure out the flight of a rocket. It tells you कि okay, essentially exhaust gases को क्या होगा तो कितनी force लगेगी rocket के ऊपर. Okay, and we'll solve this very shortly. Okay, right? Okay. Now what you are really interested in is of course dv by dt क्या. Now, but before I go on. the naive approach would have been कि m times v momentum सर m times v है आपने dv by dt निकालना है देखें मैं आपको बताता हूँ dp by dt जो है that equals d by dt of mv और Redspot के past papers in the mathematics tell me that dm by dt times v plus m times dv by dt, and this must be equal to the external force. वो तो नहीं है, तो इधर आपका प्रोजेक्ट रूल फेल हो गया कैलकुलस का। ये देखो झूठ तो नहीं बोल रहा, यही आता आएगा प्रोजेक्ट रूल लगा के। तो सोचो इसके बारे में कि क्यों फेल हो रहा है। ओके वो सही है, वो तो फर्स्ट प्रिंसिपल से मैंने निकाला है यूजिंग द डेफिनेशन ऑफ द डेरिवेटिव। नहीं ये बट द प्रोजेक्ट रूल डज इन्वॉल्व सम अजम्पशंस। मैथ्स उधर भी नहीं चेंज हुआ, टोटल मैथ्स। तो इसलिए मैं बार बार कहता रहता हूं ना, कोई एनिमलिस्टिक साउंड से मैं रेफर करने लगा था, पता नहीं रिमेंबर के क्लास में हुआ क्या है, बट एनीवे इसलिए मैं बार बार कहता रहता हूं कि डेरिवेशंस और अजम्पशंस वगैरह पे ध्यान दे दिया करो, अदरवाइज आपने कुछ और ही रॉकेट डिजाइन कर लेना था। ओके राइट, ओके ओके एनीवे सो लेट्स फोकस ऑन दैट। ओके ये आप सोचो ना इसके बारे में, अगली दफा बताऊंगा। ओके सोचो इसके बारे में। ओके लेट्स फोकस ऑन दैट। आपने निकालना क्या है, आपने निकालने के रॉकेट को होता क्या, हाउ डज द रॉकेट मूव, इन अदरवाइज गो बैक, यू आर गोइंग बैक टू द सेम थिंग। From this equation, which follows from Newton's second law for a system of particles, you can figure out the acceleration of the rocket. ये फंसी हुई है acceleration of the rocket. Once you know the acceleration of the rocket, you can figure out the velocity of the rocket. Once you know the velocity of the rocket, you can figure out the position of the rocket, and so on and so forth. Okay, so let's focus on the thing that we want to find out. M dv by dt equals Fe plus u dm by dt. And therefore dv by dt equals Fe, the external force on the rocket, divided by the mass of the rocket, plus the velocity of the exhaust gases with respect to the rocket, divided by the mass of the rocket, times dm by dt. अब सपोज को ग्रेविटी लग रही है रॉकेट के ऊपर, यू आर गोइंग टू लॉन्च ए रॉकेट फ्रॉम द सरफेस ऑफ द अर्थ, इसका क्या डायरेक्शन है? Of course, yes. I mean, अगर आपने सुपरमैन बनना है तो you have to counter the force of gravity. ये तो नीचे की तरफ ही होगी ना. This is just the gravitational force acting on the rocket. This thing is the gravitational force acting on the rocket. As the rocket hopefully flies up and up and up, this changes depending on the distance of the rocket from the center of the earth. ये Newton's law of gravitation से आपको मिलेगा. ये क्या? What's the direction of this thing? Upward or downward? Hopefully upward. Otherwise, it's the most useless rocket of all time, okay? So it should be upward. Why is it upward? How does it follow mathematically? Well, first of all, your rocket के आप exhaust gases किस तरफ फेंकोगे? ऊपर की तरफ, नीचे की तरफ? So, नीचे की तरफ with respect to what? With respect to the rocket. Rocket जो मर्जी कर रहा हो, आपके with respect to the rocket, अगर आप rocket में बैठे होगे, आपको कोई gases में नीचे की तरफ फेंक रहा हो. Just like आप अगर उल्टे तरफ गाड़ी उस तरफ जा रही है, आप हमेशा उल्टा मुंह करके फेंक जाओ पीछे की तरफ बॉल, आप विद रिस्पेक्ट टू द कार बॉल हमेशा पीछे फेंक रहे हो, बट विद रिस्पेक्ट टू द ग्राउंड बॉल हो सकता है आगे जा रही हो सकता है पीछे जा रही हो, डिपेंडिंग ऑन द वेलोसिटी ऑफ द कार. So with respect to the rocket, the exhaust gas is always being thrown downwards. So if I set up the y-axis that u will be equal to minus some number Ey, क्योंकि the exhaust gases are being thrown downwards. मैंने upward direction को positive लिया है. That's the direction of my unit vector. Hence minus some number times Ey. dm by dt क्या है? Positive या negative? Negative. The mass of the rocket is going down. So this is negative. U, the component of U is negative. तो negative negative क्या देगा आपको? So the whole thing will be pointing in the plus Ey direction.
ये जो आपने y को ऊपर positive.
हाँ, ठीक है. So this thing is basically the upwards force. ये m को निकाल दिए क्योंकि वो फिर acceleration आ जाएगी, upwards acceleration. This thing that I have drawn in a box is upward force. This is what the rocket engineers call as a thrust force. वेरी ऑफन वो आपको यू की वेलोसिटी रॉकेट इंजीनियर्स वगैरह नहीं बताते, वो आपको थ्रस्ट फोर्स की वैल्यू बताते हैं, तो भी थ्रस्ट फोर्स इस रॉकेट की इतनी है। एंड देन दे आल्सो गिव यू कि dm/dt की वैल्यू क्या है। सो दे यूजुअली गिव यू टू वैल्यूज, dm/dt की वैल्यू इन मैग्नीट्यूड, वो आपको पता है नेगेटिव ही होगी क्योंकि रॉकेट का मास ऑफ कोर्स डिक्रीज होना है, तो इसकी वैल्यू दे देते हैं और थ्रस्ट फोर्स की वैल्यू दे देते हैं। इफ यू नो दीज टू नंबर्स ऑफ कोर्स यू ऑटोमेटिकली नो कि u कितना होगा, बिकॉज u इज सिंपली द थ्रस्ट फोर्स डिवाइडेड बाय dm/dt। हाँ, वो एक्सटर्नल फोर्स में जाएगी, एग्जैक्टली वो एक्सटर्नल फोर्स में जाएगी। अच्छा, नाउ अब मैंने जो है कोई वैल्यूज नोट की थी, आई थिंक फॉर द Saturn rocket that sent man to the moon, let me open these values. अच्छा, so a rocket has total thrust force of, let me write these down. So a rocket has thrust force equals to 3.4 times 10 to power 7 newtons, okay, and dm/dt, the rate of fuel consumption, you know, इंजीनियर है तो उन्होंने ज़ाहिर बात है फैंसी बनना है, ओके, द रेट ऑफ फ्यूल कंजम्पशन इज सम नंबर, फ्यूल कंजम्पशन जितना फ्यूल कंज्यूम हो रहा है उतना ही ऑफ कोर्स मास ऑफ रॉकेट कम हो रहा है, सो dm/dt इज 1.4 times 10 to power 4 kg/second, दैट्स अ लॉट ऑफ फ्यूल। एक सेकंड के अंदर कितना kg कंज्यूम 14,000 kg in 1 second, okay? तो रॉकेट बनाना इतना आसान काम नहीं है। The initial mass of the rocket, as in the mass of the rocket when it's launched, is 2.8 times 10 to power 6 kg. So these are just the numerical values for an actual rocket, okay? And your objective now is to use this to figure out कि भाई रॉकेट की मोशन कैसा है, plot, or in other words, plot a graph of v versus t for the rocket, this rocket. कैसे करोगे? If you launch it from near the surface of the earth. Well, first of all, you know, u तो आपको given है, right? So u kind of given है because you just divide the thrust force divided by dm/dt. u itself की तो शायद आपको जरूरत ही नहीं क्योंकि ये पूरे डब्बे की वैल्यू आपको पता है, ये पूरे डब्बे की वैल्यू आपको पता है, that is just 3.4 times 10 to power 7 newtons pointing upwards. You know the mass of the rocket, but the mass of the rocket keeps on changing. So over here I am assuming that dm/dt constant है. For actual rockets are designed in a different way. कि dm/dt शुरू में काफी ज्यादा होता है, जैसे जैसे टाइम बढ़ता जाता है वो कम होता जाता है. Less fuel is burnt later on compared to the initial part. क्योंकि इनिशियली उन्होंने जल्दी से जो है उसको ग्रेविटेशन फील्ड से बाहर निकालना होता है. Once it's pretty far away from the surface of the earth, you don't need to burn much fuel to keep it going. Okay, but just to simplify the situation over here, I'll assume कि dm/dt constant है. Okay, okay, ये throughout यही वैल्यू है, ये मैं कह रहा हूँ. In real life ये इनिशियल वैल्यू के करीब है यार. Okay, और this is the initial mass of the rocket, तो फिर कैसे सॉल्व करोगे ये? This is a horrendous equation to solve. आपके एक्सटर्नल फोर्स के अंदर लॉ ऑफ ग्रेविटेशन है, लॉ ऑफ ग्रेविटेशन के अंदर y है, y is the y coordinate of your rocket measured from the center of the earth. y किस तरह चेंज हो रहा है वो v पे डिपेंड कर रहा है कि वेलोसिटी ऑफ रॉकेट के ऊपर. वेलोसिटी कैसे चेंज हो रही है वो डिपेंड कर रही है फोर्स कैसे है, वो डिपेंड कर रही है आपकी ये u dm/dt के ऊपर. एक्सटर्नल फोर्स, इन दिस केस द Fe for a rocket launched near the surface of the earth, ये minus gme capital M over y square Ey होगा. Y is the y coordinate from the center of the earth to the rocket. तो ये आप हाथ से नहीं कर सकते. आप सारे कंप्यूटर साइंस स्टूडेंट्स हो. वन बिग रीजन व्हाई there was a big advancement in computing hardware in the 1960s, क्यों इतने पैसे थ्रो किए गए थे, was precisely to solve this problem. नासा को इसलिए ढेर सारे पैसे दिए गए थे कि भाई ये इक्वेशन आप हाथ से नहीं कर सकते, use a computer to do it. So line number 3, we need to numerically solve the rocket equation, blah blah. This is exactly what I've just written down. Of course, I haven't put in the arrows on top. Comment kar never mind, it's implied. The graph, I've just initialized the graph paper. I've just initialized the curve because I want to plot the velocity, the speed of the rocket as a function of time. So all I've done is to initialize the graph paper with the time on the x-axis, the velocity on the y-axis. वो labels मैंने डाल दी. This is the mass of the earth, me, surprise, surprise. Re is of course the radius of the earth that I need to calculate the external force, which in this case is the gravitational force being exerted by the earth on the rocket. Capital G of course is your constant in the law of gravitation. Now again you have to initialize the simulation. You have to initialize the initial condition. Initially the rocket is at the surface of the earth. That is what line 18 is doing. So it's setting the initial position of the rocket to be not 0, because you are measuring, you have set up the origin of your coordinate system at the center of the earth, as is usually done when you are dealing with Newton's law of gravitation. You start off by saying that the velocity of the rocket initially is 0, okay? And then you say that, okay, you start your clock just after the rocket starts, so that is t equals to 0. You set the time interval for the simulation, कि इस time step के बाद आपने update करते जाना सारी चीजें, dt is equal to 0.001, okay? And then you say, okay, ये भी देखो, You calculate the next value from the previous value by saying that f of x1 equals f of x0 plus the derivative times the difference between x1 and x0. Then you say that the total mass of the rocket initially is this. ये इसकी value update होती जाएगी, of course. This is just the initial value. This is the rate at which r is not the radius of the earth, nothing to do with radius. R is the rate of fuel consumption. dm is then the rate of fuel consumption multiplied by dt, right? So that gives you the small change in the mass over a time interval dt. I'm assuming a dm by dt constant. So dm by dt times dt gives you dm. Okay. And dm negative hai because the change in mass is, the mass is going down. That's why I put in this minus sign over here. फिर u क्या है आपका? If you want to calculate u, you can do it. Of course, you just divide the thrust force by the rate at which the gases are expelled out. Thrust force, remember, आपकी u times dm by dt है, तो u क्या होगा? Thrust force divided by dm by dt, or dm by dt क्या है? R. So that's what you see over here. 3.4 times 10 to the power 7. This is the thrust force divided by dm by dt. Okay. Then you basically run the simulation. Okay, so I'm going to look at the motion of the rocket until 2.5 minutes after launch. Okay, you can carry it on and on and on. What I do is, first of all, I say that, okay, let's calculate this. Then I calculate this. Then I'll add them up. So this is the portion of the acceleration due to the gravitational force, जिसको मैंने a grav कह दिया. A grav equals minus, because it's pointing downwards, I'm taking the upward direction as positive, minus g times me times y square. Mass of rocket जो है वो वैसी इसमें जो है वो cancel out हो जाएगा, because the gravitational force is proportional to the mass of the rocket. You divide the gravitational force with the mass of the rocket, जो भी mass of the rocket है, that mass of the rocket will drop out. So that's why you only see the mass of the earth over here, divided by y squared. Y उसकी position है rocket की, measured from the center of the earth. A thrust is the acceleration provided by the thrust force. So in other words, you just have to calculate the thrust force divided by m, essentially. Okay, so you basically have that, you have u divided, u times r is basically gives you the thrust force, divided that by m, you get the acceleration due to the thrust force. Okay, you didn't even need to calculate u, by the way, आप directly thrust force ये सब इस्तेमाल कर सकते थे. The total acceleration is the sum of these two, hopefully positive. Otherwise, again, you end up with a fus rocket, okay? So you need for a working rocket, this should be positive, as in the rocket should be accelerating upwards. Once you have the acceleration, उसके बाद हमें ढेर सारी अपडेटिंग करनी होगी अगले टाइम स्टेप के लिए. First of all, update the velocity of the rocket by using the acceleration vector. You update the position of the rocket by using the velocity vector. Then you update the mass of the rocket. Okay? And then you do what? Okay, then you update the time. And then you put जो भी आपने वैल्यूज निकाली हैं टाइम की और स्पीड की रॉकेट की, उसको प्लॉट कर दो ग्राफ पेपर पे. एंड okay, at the end of the day you ask the program to print out the final value of time, which in this case is 150 seconds, and the corresponding value of the speed of the rocket. Okay, so let's run this. That you can now predict exactly कि भाई आपके रॉकेट की स्पीड क्या होगी after some time. This, by the way, ये क्या है? Final value, ये इतनी बड़ी? Yes, this is 150 is the value of time. मैं स्पेस डालना भूल गया था प्रिंट स्टेटमेंट में, इसलिए प्रिंट स्टेटमेंट को यहाँ वाली प्रिंट स्टेटमेंट लिखा करो. This is the value of time, this is the value of the corresponding value of the speed. So after 150 seconds, the rocket is traveling at a speed of close to 2000 meters per second. 2 kilometers per second. Okay. नहीं, वो आपको कैलकुलेट करना पड़ेगा. It's not exactly आप नहीं निकाल सकते just so. Okay. You have to do some kind of fitting essentially. Okay. Okay, ठीक है. Let's do another problem. So remember, so अब आपकी एग्जाम वाली बात मैं करता हूँ. एक तो हो सकता है रॉकेट वाला प्रॉब्लम इटसेल्फ में एग्जाम में दे दूँ, तो कहूँ कि भाई ये रॉकेट का ये देखो ये रॉकेट का कोड है. A NASA engineer has come up with a different scheme, a 2-stage rocket, जो असल में 2 stage, 2 या 3 stage होता भी है असल में. कि during the first stage this is what happens, during the second stage this is what happens to the rocket. Write a program that allows you to calculate the speed of the rocket at time t. Okay. So for example, other problems जिसमें mass change हो रहा होगा continuously, इसमें if you notice, these are problems in which the mass of the thing that you're interested in is changing continuously. मुसलसल चेंज हो रहा है mass पे. It's not something like कि बारी बारी एक बॉल को आप फेंकी जा रहे हो. It's like continuous streams of balls are being thrown out. So you have these variable mass problems, इनको variable mass problems कहते हैं, in which the object whose motion you are interested in, the mass of that keeps on changing. If you have a variable mass problem, you do exactly the same thing. Take a snapshot at time t, take a snapshot at time t plus delta t, calculate the change in momentum divided by the change in time, set that equal to the external force. Exactly, yeah. Essentially, yes. Okay, so now let's do another example. ठीक है? Let's do कि आपका जो है कि आपकी हवा कितनी फोर्स लगा सकती है. How much force can a gust of wind exert on you, or a gust of wind can exert a force on some object? So just for simplicity, imagine कि कोई डिस्क पड़ी हुई है आपकी of area A, and some air is flowing and it hits this disk. And the question is assigned, and this disk is being held in place, for example, कोई डंडा है जिसके साथ आपने कील के साथ ठोका हुआ है. Okay. What is the force being exerted by this moving air, by this wind on the disk? कैसे कैलकुलेट करोगे? कुछ तो आइडिया दे दो. Again, you have a variable mass problem. The mass is continuously changing. वो wind आई जा रही है, आई जा रही है, आई जा रही है, continuously. What's the force being exerted by the moving air, aka the wind, on this disk?
Number of particles that it moves. Density बनाएंगे.
Essentially उसी से related होगा ना. But how will we calculate it?
So you calculate change in momentum.
Exactly. So you again take 2 snapshots of the situation. Okay, time t पे कोई situation बनाओ. You look at the change in the momentum, okay, between two snapshots. So आप कहते हो okay, ये देखो, और गौर से देख लो, इसका तो जरूर ही मैं क्वेश्चन देता हूं इस किस्म का. You look at this cross section of this flowing wind. ये जो इधर जो मैंने फेस बनाया है, what's so special about this? This is essentially the slice of the wind which hits the disk time delta t later. यानी कि जो भी सारे मॉलिक्यूल्स हैं, जो भी सारे ये शेडेड वाइट मॉलिक्यूल्स हैं इधर, सारे के सारे इस डिस्क को टाइम डेल्टा टी लेटर तक हिट कर चुके होंगे. Okay, so at time, so this is at time t. At time t plus delta t, what is the situation? The situation is that that's it. Assuming that the air comes to a stop after hitting the disk. Okay, जो भी आपके हवा के मॉलिक्यूल्स है वो रुक गए हैं, वो हैं इधर, ये नहीं कि गायब हो गए हैं, बट वो रुक गए हैं. Of course, in reality, usually the air bounces back somewhat. So then you have to consider that as well. But as a first approximation, I'm assuming कि जैसे ही कोई हवा जो है इसको आके लगती है, वो वहाँ रुक जाती है. Okay. So if I consider कि भाई the mass of the air molecules at time t is delta m. Delta m ये छोटा सा mass क्यों होगा? क्योंकि delta t छोटा है ना. Delta t छोटा है, delta t का क्या मतलब है? Delta m is the mass of the air molecules that hit the disk during the time interval delta t. अगर delta t छोटा सा है तो थोड़ा सा mass of air molecules ने hit किया होगा ना डिस्क को. नहीं होता है, but it depends on the velocity. उनका नंबर भी तो बहुत ज्यादा है ना. There's a huge number of them as well. वो भी तो billions of air molecules है ना. I mean, आप हवा में खड़े हो, अच्छी खासी force feel होती है आंधी में. Okay. Okay, so the momentum over here is, the system is the air molecules over here, and the wind is blowing at a speed v. The momentum of these air molecules is momentum delta mv. The momentum of the air molecules over here is 0 because the air molecules I'm assuming have come to a stop after hitting the disk. Either हैं air molecules except that basically they have dribbled down the disk, okay, so to speak, okay. So this is 0. The change in the momentum of the air molecules is क्या चीज? हाँ, वो हो सकता है वापस गई हो, फिर वो आप इधर उसको माइनस डेल्टा एम वी कर देते. वो अगेन यू नो इट डिपेंड्स ऑन व्हाट यू आर अज्यूमिंग अबाउट. वो 2 डेल्टा एम, वो बिल्कुल सही है. ओके, बट हियर आई एम अज्यूमिंग दैट दे कम टू अ स्टॉप. वो फैक्टर ऑफ 2 का ही फर्क आता है और कुछ नहीं होता. ओके, हाँ. ओ यार गौर से देख लो, क्यों बातें करते लगे हुए हो. अच्छा, डेल्टा एम है क्या? ओके, सो अगेन you are trying to find out the force on the disk being excited by this gust of wind. Okay, so first of all आप कहते हो अच्छा force on the disk मैंने निकालनी है, so let me analyze कि भाई momentum disk का कैसे change हो रहा है. लेकिन disk को आप कहते हो well वो तो how do I calculate that? मुझे तो mass of disk given ही नहीं है. All I'm given is the speed at which the air is moving. Okay, all I'm given is the cross section area of the disk. So you say, okay, मुझे ज़्यादा information, मुझे air के बारे में पता है. I have the information regarding how fast the air is blowing, how fast the wind is blowing. So let me instead calculate the force that the disk exerts on the wind. And then by Newton's third law, that will be equal to the force that the wind exerts on the disk. ठीक है? If you calculate the force being exerted by the disk on the wind, you have calculated the force that the wind exerts on by Newton's third law. Okay, so that's why I'm focusing on these air molecules. These air molecules are those molecules that in this time interval delta t, the छोटे से time interval के दौरान आके डिस्क को आके लग जाते हैं, टक्कर मार देते हैं डिस्क को. डेल्टा टी बहुत छोटा है, इसलिए छोटा सा जो ये क्रॉस सेक्शन एरिया है, ये जो छोटा सा वॉल्यूम बना है सिलेंडर का, एनी एयर मॉलिक्यूल विद इन दिस सिलेंडर will end up hitting the disk. I'm assuming all the air molecules essentially on average are moving in that direction with speed v. ठीक है, इसकी लेंथ क्या होगी सिलेंडर की, ये क्या लेंथ होगी, v डेल्टा t ऑफ कोर्स. ये वाले सारे मॉलिक्यूल्स ने आके हिट कर जाना है ना डिस्क को. दैट्स हाउ इट डिफाइंड डेल्टा t क्या है और डेल्टा m क्या है. ओके, so the momentum of the air molecules at time t is equal to that, the momentum of the air molecules at later time equals that. Okay, how do I calculate the change in the momentum? Final minus initial, so the change in the momentum equals minus delta m times v. ये माइनस क्यों आया? Because this is the change in the momentum of the air molecules. इसको divided by delta t करोगे तो क्या आएगा आपके पास? The force exerted by the disk on the air molecules. And of course the force exerted by the disk on the air molecules must point to the left. इसलिए तो रुके हैं वो एयर मॉलिक्यूल्स आपके इनिशियली उस तरफ जा रहे थे, वो फोर्स इस तरफ लगेगी तो वो रुकेंगे ना. Okay, so delta p over delta t equals, ignoring the sign, we just know that direction उसका वो है v dm by dt, if dp by dt इसको बता. And this must be equal to the force on the air molecules. लेकिन वो फोर्स आई किधर से है, किसने ये एक्साइट किया ये हॉरिजॉन्टल फोर्स टू स्टॉप देम? द डिस्क. So by Newton's third law, this must also be equal to the magnitude of the force being exerted by the wind on the disk. So this is also equal to the force on the disk by the wind. Okay. Now अगर आप करो कि ओके ये dm by dt को सिंप्लीफाई करो, यूजुअली ये एक्सप्रेशन बहुत कॉमन होता है इन प्रॉब्लम से. The rest of the thing is how do you simplify this? That varies from situation to situation. अब आपका dm क्या है? Well, delta m किसके बराबर है? इधर आकर आओ. You can write delta m in terms of the density of the air. How do I write down this mass of these air molecules in terms of the density of the air? So rho is the density of air times the volume of the cylinder that I've drawn. Volume क्या होगा इसका? Area, cross section area multiplied by the length of the cylinder, which is v times delta t. ये याद आया वो जो आपने I is equal to navy derive किया था रेड स्पॉट में इलेक्ट्रिकल कंडक्शन के लिए. ये बेसिकली वही है एक्सेप्ट के वो इलेक्ट्रॉन्स की बजाय sea of electrons की बजाय जो है ये वो है एयर मॉलिक्यूल्स हैं इन द विंड. नेवी रो की बजाय एन की बजाय रो है, बाकी वही है, बस 4 से मल्टीप्लाई नहीं किया क्योंकि आई एम जस्ट लुकिंग फॉर द mass instead. Okay, so delta m over delta t equals rho av. Okay, you plug this thing over here and what do you get? You get rho av square. This is the force exerted by the wind on the disk. क्या लगेगा? हाँ, of course, in general. That depends on कि air molecule को collision के बाद क्या होता है exactly, और किस एंगल पे आके wind लगती है. So assuming कि वो बिल्कुल normal लग रही है और रुक जाते हैं, then that's what I find. Okay. Notice the ये एक्सप्रेशन हमको क्या बता रहा है? That the force exerted is proportional to the square of the wind speed. अगर आप गलती से YouTube वीडियोस पे कभी हरिकेन्स की वीडियोस वगैरह देखो, जो मीट्रोलॉजिकल वीडियोस हैं, उनकी तबाही वाली वीडियोस ना देखो. जो मीट्रोलॉजिस्ट वगैरह एक्सप्लेन करते हैं कि भाई विंड स्पीड्स अगर इस हद तक हैं तो दिस इज अ कैटेगरी 1 हरिकेन, इस हद तक हैं तो दिस इज अ कैटेगरी 2 हरिकेन. देयर आर 5 कैटेगरीज ऑफ हरिकेन्स बाय द वे, डिपेंडिंग ऑन हाउ मच डिस्ट्रक्शन दैट दे कॉज. कैटेगरी 4 और कैटेगरी 5 में इतना ज्यादा विंड स्पीड का फर्क नहीं है, but the destruction that they cause is very different, simply because ये v square का factor. The force exerted by the wind rapidly increases as you change the speed. If you double the wind speed, the force exerted by the wind increases 4 times. It doesn't double. क्योंकि एक फैक्टर v आया कि आपका जितनी ज्यादा v होगा उतनी ज्यादा आके हवा लगेगी, और जितनी ज्यादा v होगा उतनी ज्यादा हवा का मोमेंटम भी चेंज होगा, क्योंकि उतनी ज्यादा स्पीड से इनिशियली ट्रेवल कर रही थी, उतनी ज्यादा ब्रेकें लगानी पड़ेंगी हवा को. Okay, so there are 2 factors of V that come in. The V goes into delta M, V also goes into M times V, momentum mein. Okay, so that's why the force exerted by the wind on the disc is proportional to V square. Okay, so it makes a big difference. A small change in the wind speed can make a big difference, also in a positive sense. अगर आप कोई विंड टरबाइन वगैरह को विंड एनर्जी को यूटिलाइज करने की कोशिश कर रहे हो, a small change in the wind speed can bring about a huge positive change. Okay, let's do another one. A slightly different one. वेरिएबल मैथ्स के कर लिए, थोड़े एक कोलिजन का भी करा देता हूँ. Okay, हाँ.
विंड टरबाइन का जो फैन होता है उसकी साइड में फोर्स.
हाँ, yeah. So it's not exactly the same. It's not exact, but it gives you some idea कि wind speed की थोड़े से wind speed के change से जो है वो probably the actual physics involved for a wind turbine is much more complicated than this. Okay, ठीक है. अच्छा, anyway, वो आपको you can calculate then कि energy per unit volume कितना है wind का and energy rate क्या है and so on and so forth. Okay. Okay. अब अगला प्रॉब्लम देख लो, फिर कहोगे सर क्या हो रहा है ये. Okay. The final problem for today, actually I was going to start rotations from half an hour ago, लेकिन फिर मुझे तरस आ गया कि आपकी शक्लें देख के मिड टर्म वाली हो गया, पता नहीं क्या. You have is called the ballistic pendulum. ये कोई कैनन बॉल वगैरह या ऐसा कोई पेंडुलम नहीं है. Nothing to do with that. Okay, it's just because it's called a ballistic pendulum because. So the ballistic pendulum is a device that allows you to measure the speed of a bullet. That's why it's called a ballistic pendulum. It's a very very primitive device, as in literally एक धागे के साथ या रोप के साथ एक डब्बा जो है बांध दिया जाता है, of a material with enough stopping power such कि बुलेट अगर इसमें आए इस डब्बे के अंदर रुक जाए बुलेट. Okay. So what you do is that you fire a bullet at this block, and the bullet either, by the way, मैंने bullet की trajectory almost horizontal बनाई है. Why? क्योंकि bullet बहुत तेजी से जा रहा है, उसको curve करने का essentially time ही नहीं मिलता. The vertical distance that the bullet falls is half gt square, but the time taken for the bullet to go from here to here is so small that half gt square is very very small. So basically the vertical distance fallen by the bullet is very very small. So that's why I've drawn the trajectory as almost horizontal. In other words, अगर projectile motion में जो हमने वो trajectory की shape की equation derive की थी, उसमें u बहुत ज़्यादा value set कर दो, वो curvature उसका essentially 0 आ जाएगा. Okay. Right. So the mass of the block is m, the mass of the bullet is small m, और the idea is कि ये इसको आके लगता है, टक्कर होती है, this gets absorbed, the bullet gets stuck within the block. The whole thing, टक्कर की वजह से the whole thing swings upwards. And the only thing that the forensic scientist, अगर आपने CSI देखी है कभी तो you must know that it involves a lot of sunglasses. Okay, but anyway, so your block is going to swing up in this circular arc by height h. The idea is that measuring this height h should allow you to figure out the speed of the bullet. और वो उसके लिए इसलिए इंपॉर्टेंट है बिकॉज वो क्राइम सीन से अंदाजा लगा सकते हैं बुलेट की स्पीड से शूट हुआ था, फिर फलानी गन के साथ मैच करता है या नहीं करता, एंड सो ऑन एंड सो फोर्थ. ओके, तो कैसे निकालेंगे? हाउ डू आई रिलेट h टू u गिवन कैपिटल M एंड स्मॉल m? सो what you do is कि आप सिंपली कह देते हो ओके लेट्स यूज कंजर्वेशन ऑफ एनर्जी. उसकी जो इनिशियल काइनेटिक एनर्जी है वो हाफ m u square है. I'm treating the block plus the bullet as my system. The block is initially at rest, zero kinetic energy. The bullet is moving with speed u initially. ये आपकी kinetic energy है. All of it eventually gets converted to gravitation potential energy. Capital M plus m times And this allows you to write down that h equals to mu square divided by 2 capital M plus M times g. ये ठीक है, एक्सेप्ट के इसमें गड़बड़ है. ऑफ कोर्स इतना सिंपल नहीं था, वरना मैं कभी क्लास में ना करा रहा होता है. दाल में कुछ काला है, काला किधर है? नहीं नहीं, इग्नोरिंग एयर रेजिस्टेंस. Exactly. You are saying that all of the initial kinetic energy of the bullet got converted to gravitational potential energy. But this is an inelastic collision. आपका बुलेट तो स्टक हो गया है ब्लॉक के साथ. For an inelastic collision, you need to take the internal energy into account. But that internal energy you cannot calculate. As in half mu square will be equal to this thing plus something else. You don't know that something else, okay? तो फिर अब आप क्या करेंगे? नहीं, अभी मोमेंटम शोमेंटम की बात की है तो मोमेंटम शोमेंटम को अप्लाई करो, okay? So you have essentially that you look at अभी the momentum conserve हो रहा है, this is a collision. So the natural thing that you look at is momentum conservation. The momentum conserve हो रहा है? Of course नहीं हो रहा. बुलेट इनिशियली मूव कर रहा है उस तरफ, इधर जब रुका हुआ है बुलेट नहीं मूव कर रहा और ना ही ब्लॉक मूव कर रहा है. The initial you have a large initial momentum, you have zero final momentum. तो मोमेंटम कैसे कंजर्व हो रहा है यार? लेकिन फिर अर्थ के मोशन को हम क्या करें? ओके, वो टाइम ड्यूरेशन को भी करना पड़ेगा. यू डोंट नो द टाइम. वो उसे नहीं होगा. अगर आपके मोमेंटम नहीं कंजर्व हो रहा, लुक एट सम अदर कि शायद किसी और टाइम इंटरवल के लिए मोमेंटम कंजर्व हो रहा है. Look at the linear momentum of the block plus the bullet just before the collision. Look at it just after the collision. वो कंजर्व होगा because during that little time interval external force कितनी लग रही है? External force अगर लग भी रही है वो time interval वो छोटा है. So the change in momentum is very very small. The bullet hits the block. It essentially changes the linear momentum of the block. There's an inelastic collision. You can look at, you can calculate कि किस स्पीड के साथ ब्लॉक बुलेट इकट्ठा मूव करने शुरू करते हैं ऊपर की तरफ. अब कन्वर्जन टू इंटरनल एनर्जी हो चुकी है. नाउ एनर्जी विल बी कंजर्व्ड. कि एक दफा मूव करना शुरू कर दिया, अब जो मूव करने शुरू उस स्टेज से शुरू में जो एनर्जी है, ऑल ऑफ इट गेट्स कन्वर्टेड टू ग्रेविटेशनल पोटेंशियल एनर्जी. फिर इंटरनल एनर्जी आप निकाल सकते हो. इनिशियल काइनेटिक एनर्जी को माइनस कर दो. हाँ, इनिशियल काइनेटिक एनर्जी को माइनस कर दो फाइनल ग्रेविटेशनल पोटेंशियल एनर्जी से. हाँ, क्योंकि इनइलास्टिक कोलिजन है ना, क्योंकि वो एनर्जी फॉर्म, क्योंकि आप एनर्जी कंजर्वेशन अगर लगा रहे हो, यू हैव टू टेक ऑल द रेलिवेंट फॉर्म्स ऑफ एनर्जी इनटू अकाउंट. आपकी ये श्योर, लेकिन कई केसेस में इंटरनल एनर्जी की कॉन्ट्रीब्यूशन बहुत छोटी होती है. इस केस में गारंटीड है कि छोटी नहीं होगी क्योंकि इनइलास्टिक कोलिजन है, क्योंकि स्टक हो गए. जब भी दो चीजें चिपक जाती हैं, जो है इनइलास्टिक कोलिजन. इधर चिपक गया ना ब्लॉक के अंदर बुलेट. क्या चीज? क्योंकि इनइलास्टिक कोलिजन है. एंड यू कैन कैलकुलेट कि इंटरनल एनर्जी में कितनी कन्वर्जन हुई है, अच्छी खासी आएगी. ओके, कैलकुलेट करके दिखा दे. ओके, okay, so we are going to apply momentum conservation just before the collision, just after the collision. Okay, so just before the collision, the bullet essentially is moving with speed mu. The block is stationary. So the momentum of the system before the collision is mu. The momentum of the system just after the collision क्या है कि बुलेट और ब्लॉक अब इकट्ठे जो है स्पीड v के साथ मूव करना शुरू हो गए हैं हॉरिजॉन्टली. ऑफ कोर्स देन सम टाइम लेटर दे आर गोइंग टू स्विंग अप इन दिस सर्कुलर आर्क. ये v कैसे निकालूंगा मैं? नहीं, वो तो एक्सपेरिमेंटली है, बट फॉर मोमेंटम कंजर्वेशन. ओके, this is essentially the linear momentum of the block plus bullet system just after the collision. So you have v is equal to m over ठीक है. अच्छा, अब ये जो एनर्जी है, ये जो स्पीड है, this corresponds to some kinetic energy of the block plus the bullet system. All of it will get converted to gravitational potential energy. So now you have the second phase of motion. So you have essentially divided the motion into two phases. Just before the collision and just after the collision, phase 1. For that phase, momentum is conserved. Once this phase is over, all the conversion to internal energy has taken place because the inelastic collision is complete. Now you have phase 2. Phase 2 के अंदर जो भी kinetic energy बच गई है इस system की, all of it gets eventually converted to gravitational potential energy. So you have then from here that you have half in phase 2, half plus equals the kinetic energy at the start of the second phase equals the final gravitational potential energy. M plus M cancels, and you have that V square will be equal to 2gh as verified in numerous places by red spot as well, equals V square equals M over capital M plus M. And now you can solve for U. एक दफा U के लिए आप solve कर लो, you can find out the initial kinetic energy. You have the final gravitational potential energy. Final gravitational potential energy और initial kinetic energy का difference ले लोगे तो क्या मिलेगा आपको? And you'll find that कि वो zero नहीं है बिल्कुल भी, वो अच्छी खासी है. Okay? So whenever you're looking for something is conserved or not, if something is not conserved, redefine your system, redefine the initial, what you mean by initial and final and so on and so forth, okay?